We're always hearing about these giant, world-changing AI models, right? But what happens when they get things completely, totally wrong? Well, a lot of the time, the problem isn't the AI, it's the data. Today, we're diving into data transformation, the secret sauce that turns messy, raw data into high-octane fuel for machine learning.
So, imagine you've built a state-of-the-art algorithm, but its predictions are just awful. Why? You'd be surprised how often the answer has nothing to do with the model, but everything to do with the data we fed it. Even the most powerful models can fail, and fail spectacularly if the data isn't prepared just right.
Okay, let's make this super clear with an example. Imagine a model is looking at two things: a person's age, which might be between 18 and 70, and their salary, which could be up to, say, $150,000. Now, to you and me, those are just two different concepts. But to a machine, 150,000 is a ginormous number compared to 70. Without any guidance, the model will just assume salary is thousands of times more important than age simply because the number is bigger. And that is where everything starts to go off the rails.
And this brings us right to the heart of the matter, what we call the unbalanced data problem. When your data features are on wildly different scales or in totally different formats, machines get biased. They misinterpret what's important, and that leads to some really inaccurate and unreliable results. So, how do we fix it? The fix is called data transformation. And really, it's just the process of converting our data into a clean, consistent format that a model can actually work with. It's all about improving accuracy, fixing those skewed ranges we just talked about, and, at the end of the day, making our data speak the language of machines. To pull this off, data scientists have a pretty essential toolkit. Today, we're going to open it up and look at the three most important tools you'll find inside: scaling, normalization, and encoding. These three are the real workhorses of data preparation.
All right, first up, let's deal with those numbers. The main goal here is to get all of our numerical data onto the same scale so our models can make fair comparisons.
This process is called scaling, and it's all about adjusting the range of our features so they're on a similar level. This is absolutely crucial for any algorithm that measures distance between data points, like k-nearest neighbors, or for models that learn in small steps, like neural networks. If you don't do this, the features with the biggest numbers will always shout the loudest and just completely dominate the entire learning process. And what's really cool here is that there's no single best way to do this. The right method really depends on your data. If your data looks like a classic bell curve, standardization is your best friend. For things like neural networks or image data, where you need values in a strict 0 to 1 range, min-max scaling is perfect. But what if your data is messy and has some crazy outliers? Well, that's when you bring in robust scaling. It uses the median, the middle value, so it doesn't get thrown off by those extreme numbers.
Now, you're also going to hear the term normalization thrown around. And while it sounds a lot like scaling, there's a key difference. Instead of just squishing the range of the numbers, normalization is all about focusing on the direction of the data. Think about it for text analysis. We might care more about how words relate to each other in a sentence, not just how many times they appear. That's where normalization really shines.
Okay, so we figured out how to handle numbers, but what about words? The next big challenge is translating categories, text labels, into something a machine can actually process.
I absolutely love this quote because it just hits the nail on the head. Our models don't get red or green, but they definitely understand numbers. So this process of translating categories into a numerical format, that's called encoding.
So let's ask that question directly. How does a computer take a simple list of colors and actually process it mathematically? Well, the most common answer is a really clever technique that avoids creating a false sense of order.
And here it is, the clever solution: one-hot encoding. See, your first thought might be, why don't we just label red as 1, green as 2, and blue as 3? But you can't do that. That would accidentally teach the model that blue is somehow more or better than red. So instead, we create a new column for each color and just use a 1 or a 0 to show which one is there. It's a clean, simple way to represent categories without inventing a hierarchy that doesn't exist.
And just like with scaling, the right encoding method totally depends on your data. If your categories have a natural built-in order, like small, medium, and large, then something called ordinal encoding works perfectly. But for categories with no order at all, like our colors, one-hot encoding is absolutely the way to go, so you don't trick your model into seeing relationships that aren't really there.
So we've got our tools for numbers and our tools for words.
how do we put it all together into something that actually works? Let's walk through a practical workflow, a kind of master recipe for data transformation. When you put it all together, it looks a lot like this data pipeline. It's a really logical flow. First, you got to understand your ingredients, figure out which columns are numbers and which are categories. Then comes the cleanup phase. You handle missing values, you fix any crazy outliers. Only after all that's done do you move to the core transformation, applying scaling to your numbers and encoding to your words. Finally, with everything prepped and ready, you feed that beautiful, clean data into your model.
Okay, I know this can all seem like a lot of tedious, behind-the-scenes work, but what's the real impact? Why is it so incredibly important to spend time on this?
Well, here it is. This is the payoff. Proper data transformation isn't just some minor tweak. It can improve your model's performance by a staggering 30 to 60%. I mean, that's huge. That's often the difference between a model that's completely useless and one that's genuinely revolutionary.
So the biggest takeaway here is this. Data transformation isn't just about cleaning. It's about building a solid, reliable, and fair foundation. Without it, even the most advanced AI in the world is basically being built on quicksand.
And that really leaves us with a final thought to chew on. We always hear that phrase, data is the new oil. But raw crude oil, straight out of the ground, it's pretty much useless. It's the refinery that turns it into something valuable. So, if that's true, maybe the refinery, this whole process of transformation, is actually the most important part of the entire operation.